Hello friends, today I am going to talk on the topics complex numbers, which is the first chapter for 11th Arts and Science of SSC Board Maharashtra State Board. Due to the corona problem, our students are at home presently, and so my friends, my relatives requested me to take few sessions for mathematics. So myself, Professor Divate BB, will take few sessions on maths paper 2, and my friend Dr. P.G. Jadhav from Alefata College will going to take topics from maths paper 1. So today we'll start the complex number chapter. You are well familiar with set of natural numbers which are studying from first school level, that is from first standard. After natural number, you come across the concept set of whole numbers. Just by inserting 0, you get that one. If I enclose this list in curly bracket, it is a set. So set of whole numbers is 0, 1, 2, 3, etc. Then you have studied concept of integers, which is denoted by Z or I, and it contains natural numbers 1, 2, 3, so on, whole number 0, and negatives of natural numbers -1, -2, etc. After that, you come across set of rational numbers in 6th or 7th standard, fractions. So number of form, say 2 by 3, 3 by 2, 11 by 6, 2 by 1, one integer upon other integer, where denominator not equal to 0. That type of number is known as rational number. So P by Q, where PQ are integers and Q not equal to 0. I can take Q to be natural number only. Q to be natural number only. Real number, irrational number. You have to study Search. A rational number whose nth root is not a rational number, whose nth root is not rational number, then that nth root of that rational number is known as surd. And that are also numbers which are represented on line by point. If I take some line, say 0, 1, 2, 3, and so on, -1, -2, here I will represent the integers. Between 0 to 1, I have, if I partition set into 10 parts, equal parts, and so on, I will get here 1 by 10, 2 by 10, 3 by 10, etc. But that are in form P by Q. So that are also rational numbers. In other intervals, n to n plus 1, we will get also rational numbers by dividing intervals into n number of partitions. You will get rational numbers. But even though there gaps remains between two rational numbers also, and there is no any gap between 2 points on line, this line is continuous. That other points, the points which are represented by P by Q form, that are rational number on this line, and which point remains there, that points also represent numbers that are known as irrational numbers. That are known as irrational numbers. So what is the irrational number? This is your real line, irrational number. A number which is not rational, or I will say that real number which is not rational. Okay, so if I take root 2, root 3, then say 2 by 3 raised to 1 by 4, 11 by 5 raised to 7 by 5, fifth root of 11 by 5 doesn't exist, and so on. Are irrational numbers. We cannot write these numbers in P by Q form. I am not interested to show how they can't be expressed in this form. So every point on line represents a real number, and conversely, every real number is represented by some point on this line. This line is known as real line. Real line. And collection of all rationals and irrationals. Collection of all rational and irrational. Collection of all rationals and irrationals is known as set of real numbers. Set of real numbers. So what is this set? Natural number set. This is whole number set. This is integer set. This is rational number. R is a union of set of rationals and irrational numbers. Till we are not studied sets in detail, so I am not talking about union, operations on set, etc. So now, in 9th or 10th standard, we have studied the quadratic equation. Quadratic equation. We have studied linear equation. So ax plus by is equal to c, where a or b not equal to 0 in R is lying linear equation. Why this is linear equation? In this equation, degree of variable x and y is 1. ABC are real numbers. ABC are real numbers. 2x plus 3y is equal to 7. 7x minus 4y is equal to 2. Half x minus root 2y is equal to 0. Those represent lines. And you have studied how to plot that lines in a plane in 9th standard. Then you have come across quadratic equation. So equation of type x square plus bx plus c is equal to 0. Where a not equal to 0, ABC are real numbers. This is known as quadratic equation. For example, 3x square plus 5x minus 7 is equal to 0. If I take x square plus 1 is equal to 0, x square plus x plus 1 is equal to 0. In this equation, if coefficient of x is 0, constant term is 0, even though it is quadratic equation. What we want, coefficient of second degree term, that is x square, must be non-zero. X square must be non-zero. Then that equation is known as quadratic equation. I am introducing quadratic equation here. Now, if I take the quadratic equation, you know that for quadratic equation x square plus bx plus c is equal to 0. You have defined discriminant del is equal to b square minus 4ac. If this is, if 1 del is equal to del greater than 0, then roots or solution, then roots of 1 are real and distinct. Real and distinct, which are studied in 9th standard. Secondly, if del equal to 0, discriminant is 0, then roots are real and equal. Okay. And third, if del less than 0, then roots are not real. Roots are not real. Okay. Roots of 1 are given by, x is equal to minus b plus minus under root of b square minus 4ac, that is this del. upon 2a. Okay. So if b square minus 4ac is negative number, we know that square root of negative number doesn't exist, as square of any real number is greater equal 0. It is never negative number. So if I take equation, say simple equation here, x square plus x plus 1 equal to 0, or before that if I take just x square plus 1 equal to 0. If I take this quadratic equation, for any x belongs to R, x square is greater equal 0. Square of any real number is non-negative number. Therefore, your x square plus 1 is greater equal 1 for every x belongs to R. This is symbol for every, for any, for each. So x square plus 1 greater equal 0. And therefore, x square plus 1 is not equal to 0 for every x belongs to R. Not equal to 0. This equation has no root in set of real number. What this implies is x square plus 1 equal to 0 has no root in set of real number. Then now x square plus 1 is equal to 0 implies x square is minus 1, but x square is not minus 1 in set of real number. So if I take square root on both sides, we will get square root of minus 1 plus minus. This is not a real number, so denote it by I symbol. This I is called as, this is the Greek letter iota. Greek letter iota. Introduced by Leonard Euler. He is mathematician. He introduced this I symbol for square root of minus 1 firstly, and he used that I and minus I are roots of equation x square plus 1 equal to 0, which are not real roots, which are not on real line, which are represented by just line. On that, this plus minus I numbers are not there. This I symbol is iota, and this I gives rise to new number system, new numbers which are complex number, which are complex numbers. So what is our complex number? For AB belongs to R, a number of form Z equal to A plus IB, where I equal to square root of minus 1 is called as complex number. Is called as complex number. Set of all complex numbers. Set of all complex numbers is denoted by C, first letter of complex C, and therefore what is your C set? It is number of type A plus IB, where A and B are real numbers and iota is equal to square root minus 1. Square root minus 1. Now, if B is 0, okay, note for B equal to 0, for B equal to 0, Z is equal to A belongs to R, Z equal to A belongs to R, implies R is subset of C. And if I take 1 plus I into 1, B is non-zero, then there exist complex number which are not in R, therefore R is proper subset of set of complex number. So I am using terminology is proper subset, subset, etc. So we'll study that concept detail in set chapter. Okay. So set of real numbers is a subset of set of complex number. We know that a natural number is subset of whole number is subset of integer is subset of rational number, and rational number is subset of real numbers, real number is subset of C. Okay, so note N is contained ring, W is contained ring, Z is contained ring, Q is contained in R, and R is contained in set of complex number. Okay. Now, for complex number, Z is equal to A plus IB. What is this A? A is real part of Z. Real part of Z, and it is written as Re dot Z. This B, just B, is imaginary part of Z. Imaginary part of Z. And it is written as Im dot Z. Im dot Z. Real and imaginary part. Then on number system, you know how to add two numbers, subtract two numbers, multiply two numbers, divide one number by other. So, as for complex number, A and B are real number, and additions for real number, multiplication for real numbers is defined. So, it is possible to define operations on set of complex number, addition, multiplication, division, etc. So, see now operations on complex numbers. Operations on C. So let Z is equal to A plus IB, and say Z1, Z2 is equal to C plus ID belongs to set of complex number. Then first operation, Z1 plus Z2, Z1 plus Z2 is equal to. Now you know how to add 2x plus 3y is equal to 5, 7x minus 6y is equal to say 11. In addition, what you are doing, you are adding like terms. Like term means x terms together, y terms together, constant term together means 9x, 3 minus 6 minus 3y, 11 plus 5, 6. For quadratic equation, if I have x square minus 5x plus 7 minus x square plus 11, if I to take addition of these two polynomials, in this what are the like terms? X square. So we'll get x square minus x square. So this is a plus sign here, plus, then plus minus 5x plus 7 plus 11. Means you are adding like terms. So for the Z1 and Z2, which are like terms? Real part are like terms, imaginary parts are like terms. So while taking addition, you have to take addition of real parts, A plus C, and addition of imaginary part plus I times B plus D. So this is the way of defining addition operation. For difference, we'll just get here A plus IB minus in bracket C plus ID, opening bracket there, we'll get A minus C, B minus D here. This is the difference operation. Second operation, Z1 into Z2, or we like this as to be separate. Z1 minus Z2 is equal to A minus C plus I times B minus D. Third operation, Z1 Z2, A plus IB into C plus ID. So while taking product, what you are doing? You are multiplying second bracket by first, again second bracket by second. So we'll get A into C plus ID plus IB into C plus ID. This is nothing but AC plus I times AD plus I times BC plus I square BD. But what is your I square? I square is minus 1. So I square is minus 1. So we'll get AC plus I times AD plus BC minus BD. Now A, B, C, D are real numbers, so AC is a real number, BD is a real number, so this is nothing but AC minus BD plus I times AD plus BC. Okay, so this is your multiplication operation. Okay, so what is happening here? You are taking AC, then BD, and minus sign is there. AC minus BD. For I term, you are taking AD and BC. This is for I. This is for real part, real Z, and this is for imaginary part. So in this way, you are taking the product of two complex numbers. For 1, for Z2 not equal to 0, C plus ID not equal to 0. Z1 upon Z2 is equal to A plus IB upon C plus ID. Now what is the complex number? Is of type A plus IB. Denominator never contain your iota term. So we don't want this C plus ID in denominator. So what we'll do? We'll multiply its numerator denominator by C minus ID. A plus IB upon C plus ID into C minus ID upon C minus ID. Just like as rationalization. And then we'll get A into C, AC, okay. Then minus I AD plus IBC minus I square BD upon C square, okay, minus I square D square. Then your I square is minus 1. So minus minus become plus. So AC plus BD minus or plus I times BC minus AD. I square is minus 1. So C square plus D square in bracket, since I square is minus 1. So in this way, your quotient operation is defined. So while taking the product of two numbers, while taking quotient of two numbers, you have to just follow this procedure to find their products and quotient division. Right? Now, we'll study the properties of these operations. Examples are two simple on operations. Okay. Property. So let Z1 and Z2 belongs to C. Then first Z1 plus Z2 is same as Z2 plus Z1, and Z1 Z2 is equal to Z2 Z1. That is addition and plus and addition and multiplication of complex numbers are commutative operations, are commutative. So this is nothing but commutative law. Second, associative. If I take three numbers, Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3, you can easily verify these properties. For multiplication also, Z1 Z2 into Z3 is equal to Z1 Z2 into Z3. These are known as associative law. Addition, multiplications are associative. If you interchange the position of bracket, you will get same answer. Third, existence of identities. Existence of identities. In that again, one, there exists 0 is equal to 0 plus I, 0 belongs to C, such that Z1 or such that A plus IB plus 0 plus 0I, I0 is same as A plus 0 plus I times B plus 0, which is equal to A plus IB for any Z belongs to C. And therefore 0 is equal to 0 plus 0I belongs to C is additive identity. Instead of real number, we know that if I add 0 in any real number, we get same number. We get same number. Fourth one, existence of multiplicative identity. There exists 1 is equal to 1 plus I0 belongs to C such that Z, such that for Z is equal to A plus IB belongs to C, whatever that complex number, Z into 1 is equal to A plus IB into 1, and this will become A into 1 plus IB1, that is A plus IB. Okay. As commutative law holds, therefore Z1, Z into 1 is same as 1 into Z, and therefore 1 belongs to C is multiplicative identity. Multiplicative identity. Inverse. Existence of inverse. In that A, for Z is equal to A plus IB belongs to C, there exists minus Z is equal to minus A minus IB. For A plus IB belongs to C, A and B are real numbers. So for that A minus A is negative real number. For B, its negative is minus B. So by using that negatives, I am writing minus A minus IB in C such that this is symbol for there exists such that Z plus minus Z must be 0. Must be 0. And therefore, minus Z is equal to minus A minus IB is a negative of Z is equal to IB belongs to C. Right? In that B, for Z is equal to A plus IB belongs to C minus 0. C minus 0. There exists 1 by Z is equal to 1 upon A plus IB, which is nothing but A minus IB upon A square plus B square belongs to C such that Z into Z bar, there exists Z inverse. Z into 1 by Z is 1. Okay. And therefore, 1 by Z, which is nothing but A minus IB upon A plus IB, A square plus B square. This is actually A upon A square plus B square plus I times minus B upon A square plus B square belongs to C is multiplicative inverse of multiplicative inverse of Z is equal to A plus I of non-zero Z belongs to C. For 0 there is no multiplicative inverse. For 0 there is no multiplicative inverse. Then sixth one, distributive laws. distributive laws. So firstly we have taken commutative law, then second associative, third identity. I think this is fourth, this is fifth. Okay, distributive laws. For any Z1, Z2, Z3 belongs to C, you can easily verify that Z1 into Z2 plus Z3 is equal to Z1, Z2 plus Z1, Z3. Okay. And more, for any Z1, Z2 belongs to C, A, Z1 plus Z2 is always complex number, and B, Z1, Z2 is also complex number. These are known as closure axioms. Closure axioms of addition and multiplication. So these are the properties of addition and multiplication. Addition and multiplication. We are not going to, if I take difference operation, difference of two complex number must be complex number. But for two complex numbers Z1 and Z2, Z1 minus Z2 may not equal to Z2 minus Z1. In fact, must not equal. Only if I take Z1 and Z2 equal to 0, then 0 minus 0 is 0. Okay? Only for that equality is there. Or no, if I take both numbers to be same, Z1 equal to Z2, that is Z, then Z minus Z is 0. In reverse way also that is 0. But if I have two distinct numbers, then the difference is not commutative. So in general, difference of two complex numbers is non-commutative operation. Similarly, division of complex number is also non-commutative operation. So in example, you have to apply all these properties while solving examples. Now, while solving the examples, powers of I plays very important role. Powers of I. So we'll take I raised to 0 is 1, I raised to 1 is I square is minus 1, I cube is equal to I square into I, that is minus I, and I raised to 4 is equal to 1. I square into I square, that is 1. Okay. Now for any n belongs to, set of natural number, I raised to n is written as I raised to 4q plus r, where q is quotient when n is divided by 4, when n is divided by 4. And r is remainder. So divide your n by 4 and find the remainder. Okay. For any n belongs to n, I raised to n is I raised to 4q plus r. Okay. Is equal to, this is equal to 0, 1, 2 or 3. Okay. And therefore, I raised to n, what will be your I raised to n is equal to I raised to 4q into I raised to r. But this I raised to 4q is same as I raised to 4 raised to q into I raised to r. That is 1 raised to q into I raised to r, which is equal to I raised to r. And this I raised to r is again 1 if remainder is 0, means if n is multiple of 4, remainder is 0. We will get I raised to n to be 1. It is I, if r is 1, remainder is 1. I square, okay, I square is equal to minus 1 if r is equal to 2. And I cube is equal to minus I if r is equal to 3. So these powers are very important while solving the examples. So with this discussion, today we'll stop our session here. I am very thankful for listening this session with patience. Okay. In next session, we'll take the example parts depending on this discussion. Thanks. Bye-bye.